We said that kinetic energy, if something is moving, has a mass, is 1/2 mv squared, and the unit of that is joules. And then we define work, W, for constant force is just magnitude of the force times displacement magnitude times cosine of the angle between them. Cosine phi, if force is this way, cos phi in general with the displacement. And we said that if force is different, it changes direction or magnitude, then dW is F dot dl, and the work total is integral of F dot dl. It's adding all the pieces together. And unit of work is also Newton meters, and Newton meters turns out to be the same as joules, right? And so they have the same units. And then we said that the net work acting on something, net, is equal to change of its kinetic energy. That was very important result. This was work energy theorem. Net work done on an object is equal to changes in kinetic energy. We derived that mathematically. This net work is work of the net force, which can be also interpreted as the sum of the individual works done by individual forces separately. Okay, net work, and or W net if equals W1 plus W2 plus W3 and so forth, if the net force equal to F1 plus F2 plus F3 and so forth. Right? So if F net is made up of these individual forces, W net is sum of the W's, because the dot product is distributive. Remember, for example, if you have 2 F1 plus F2 dot displacement, for example, is equal to F1 dot D plus F2 dot D. Right? Because of this. See, this is the net force dot D. This is work of the net force. This is work of the first one. This is work of the second one, and so forth. Right? So we have this kind of situation. You can either look at it as the work done by the net force, or the net work done by individual forces. Some of this may be positive, some may be negative. They add up like scalars, because if you remember, dot product is a scalar. So the work is a scalar. They add up like scalars. All right? And then we talked about the work for specific forces, like force of gravity. So work done by force of gravity, Wg, is equal to negative mg delta y. And y final minus y initial. How much you go up, right, in the vertical direction. And that is, of course, when your y direction is upward, right? And then we said that W for the spring is what? Who remembers that one?
1/2 kx squared.
Negative 1/2 kx squared, which is in general x2 squared minus x1 squared if you go from x1 to x2. But if you go from equilibrium, is x1 is 0 to x, x2 is x, becomes negative 1/2 kx squared. Right? So these are what we had so far. Then we applied it to some special cases. For example, when the pendulum is swinging, you want to find the final speed. All right, now I have a question. Suppose there is a building on the flat ground, right, from height h. You throw 3 different stones, small stones. One horizontally goes like this, with the speed v naught. One at that angle, theta, upward, it goes like this, right? and another one with the same angle below horizontal, with the same, all with the same initial speed. This one goes this way, right? This is also theta, below horizontal. This one goes like this one goes like that, this one goes up and goes like that. Let's call these A, B, and C. We want to rank A, B, and C according to the speed they have just before hitting the ground. This be A. This speed. Rank. What do you think?